Okay, so I work for Graham Cooks, who is a professor of chemistry at Purdue. And so Graham is well known in the mass spectrometry community, and mass spectrometry's workhorse for chemical analysis. And so one of the things you start to realize about Graham when you work for him is he doesn't like doing what everybody else is doing. So let me tell you what everybody else is doing with quadrupole ion traps, which are one kind of mass spectrometer. So what everybody else does is they vary a high voltage trapping waveform, which they call the RF. So this is a kilovolt signal that traps ions in a trap. And so the linear ramp at the end is what is the mass scan. That's where you get your chemical information, mass spectrometry. Think of it as mass. And so it turns out that requires high precision and linearity. And ramping a kilovolt signal linearly with high precision turns out to be very, very difficult. And so there's another option here, and that is to vary the AC frequency. And the AC is a low voltage signal. It's maybe a few volts. And so it turns out varying the AC does the same thing as varying the RF amplitude. So instead of varying a kilovolt amplitude, we're varying a low voltage frequency. And so this makes more sense in the context of a miniature mass spectrometer. And if you think about the restraints placed on a miniature system, you think about they have to be lightweight, you'd like it to be robust, to have ambient ionization capability, lenient vacuum conditions because you want to use small vacuum pumps, MSN capabilities for structural elucidation so you can tell what your molecule is. But most importantly, you need it to be small, you need it to have low power consumption so it can operate on battery, you need it to be simple, and you need it to be flexible. And so, do you want to vary the high voltage kilovolt signal, or do you want to vary the frequency of a low voltage signal? Well, the answer is obvious. You vary the AC frequency because that's much easier, it's much simpler electronically, and it saves power. So if you do a direct comparison of the RF amplitude scanning, which is what everybody else does, companies like Thermo and Bruker, as well as smaller mass spec companies, versus the AC frequency scan, you start to realize that simplicity is not the only advantage here. So since the precision is needed in the frequency domain for a low voltage signal, it's much simpler, but you also get extended mass range, so you can start working with higher mass proteins and polymers and things like that. It extends the range to analyze. You can analyze with a mass spectrometer. Lower power consumption, which is really nice for people like NASA scientists who want to put a mass spec on Mars, and they only get solar power to use. It's much easier to have a constant RF than a linearly ramping RF. And it turns out you can use ions more efficiently, but perhaps more importantly, you get new scan modes. And so we've invented a whole suite of scan modes from the simplest mass scan mode that's available in mass spectrometers, which is linear AC frequency sweep. Unfortunately, that has a nonlinear mass calibration, so it makes it quite difficult to interpret data. So we invented the inverse Q scan, which simplifies calibration, and that's important for anybody in analytical chemistry. There's also a whole other suite of scan modes. Periodic scanning, which increases your scan rate. Basically, you can keep up with chromatography, gas chromatography, and liquid chromatography, which often mass spec can't do that. You can do what's called a multi-scan, that is, get a full scan mass spectrum as well as get product ion information simultaneously. But you can also do precursor and neutral loss scans in a single ion trap.